Introduction to Critical Control Management, CCM. The global mining and metals industry has significantly advanced its health and safety performance, aligning with the International Council on Mining and Metals, ICMM, principle of continuous improvement. This progress is crucial in an industry where safety is paramount, with companies continually striving to reduce incidents and protect their workforce. This guide offers practical advice on preventing serious health and safety incidents, specifically focusing on material unwanted events, MUEs. It addresses how to identify and manage critical controls that either prevent an incident or minimize its consequences. Historical data shows that while risks are often known, controls are not always effectively implemented, leading to preventable major incidents. Purpose of CCM and MUEs. Critical Control Management, CCM, is a systematic approach to managing the risk of material unwanted events, MUEs. It ensures that crucial controls are in place and functioning effectively. This approach is widely adopted in high-hazard industries, providing a structured framework for risk mitigation. The primary aim of CCM is to prevent serious incidents or minimize their consequences. This involves identifying critical controls, assessing their adequacy, assigning accountability for their implementation, and verifying their effectiveness. For instance, in mining, preventing a catastrophic rockfall or a major equipment collision would be a key focus of CCM. Key definitions: hazard, risk, unwanted event. Understanding key terminology is fundamental to effective critical control management. A hazard is anything with the potential for harm, such as an energy source that, if released, could cause damage to people, assets, or the environment. For example, stored energy in a pressurized system is a hazard. An unwanted event describes a situation where a hazard is released in an unplanned way, potentially leading to consequences. Risk is the chance of such an event occurring and its impact on objectives, typically measured by likelihood and consequences. For instance, a gas leak, unwanted event, from a pressurized system, hazard, carries the risk of explosion, consequence. Key definitions: control, critical control. A control is an act, engineered object, or system designed to prevent or mitigate an unwanted event. These can range from physical barriers to procedural steps. For example, a guardrail on a platform is an engineered control. A critical control is a control that is crucial for preventing an event or significantly minimizing its consequences. Its absence or failure would drastically increase risk, even if other controls exist. A control is also critical if it addresses multiple unwanted events or consequences, making it a high-priority safety measure. The 9 steps of CCM. The critical control management process is structured into 9 distinct steps, designed to systematically manage health and safety risks. 6 of these steps are dedicated to planning the CCM program, ensuring a thorough and well-thought-out approach before implementation begins. The final 3 steps focus on the practical implementation of the CCM program. It's important to note that the process is iterative. Feedback loops, such as the one from Step 7 to Step 6, allow for revisiting earlier planning stages if site-specific conditions or control performance deviate from initial assumptions. This adaptability ensures the CCM remains effective and relevant. Step 1. Planning the process. The first step in CCM is to develop a comprehensive plan that outlines the project's scope, objectives, responsibilities, and timelines. This foundational planning ensures that all stakeholders understand their roles and the overall direction of the initiative. For example, defining who is responsible for risk assessments is critical. Key actions in this step include defining the organizational context, setting clear project objectives, and identifying the business sections involved. It also involves developing methods for identifying hazards, assessing risks, reviewing MUEs, and selecting critical controls. This meticulous preparation is vital for successful implementation, much like an architect's blueprint for a building. Organizational readiness for CCM. Successful CCM implementation requires significant organizational maturity, including the right skills, experience, and resources. Senior executive support is a fundamental characteristic, as their commitment drives the initiative forward and ensures its long-term success. Without this, even well-designed plans can falter. Organizations unsure of their readiness can use tools like the CCM Journey Model and Mapping tool to assess their current status. This tool helps identify the required foundation and provides a roadmap for increasing control management culture and practices. For instance, a company might discover it needs to invest more in training or technology before fully adopting CCM. Scoping and project deliverables. Scoping the CCM project involves defining critical aspects such as the organizational context, project objectives, and specific deliverables. This includes identifying which business sections and individuals will be involved, and over what time frame the project will be executed. A clear scope prevents mission creep and ensures focused effort. Key questions to consider during scoping include how to identify potential hazards and unwanted events, assess risks, and define criteria for material unwanted events, MUEs. It also covers methods for reviewing MUE controls, selecting critical controls, and defining their performance requirements. Adequate resources, including leadership, facilitation, and budget, are essential for a major initiative like CCM. Step 2. Identify material unwanted events, NUEs. The second step in critical control management is to identify material unwanted events, MUEs, that require focused management. This involves understanding major hazards and their potential to escalate into MUEs. For example, in mining, a major hazard like ground instability could lead to an MUE such as a catastrophic collapse. Key actions include applying selection criteria to MUEs with a strong emphasis on their potential consequences rather than just likelihood. It also involves identifying opportunities to address hazards, reduce potential consequences, and describe the identified MUE, including the relevant hazard, mechanism of release, and nature of the consequences. This detailed understanding is crucial for effective control design. Materiality criteria and MUE examples. Identifying MUEs requires considering both historical and foreseeable events, specific to individual sites and industry-wide data. This ensures that rare but potentially disastrous incidents are not overlooked. For instance, while underground methane ignition by lightning is rare, its catastrophic potential makes it a foreseeable MUE. Materiality criteria define the threshold for a risk to be considered material, primarily based on the maximum foreseeable loss or consequence. This approach helps overcome individual biases regarding event likelihood, especially for low-probability, high-consequence events. Examples of typical mining and metals MUEs include aviation incidents, underground ground control failures, heavy mining equipment accidents, and hazardous material releases, all of which have significant potential for harm. Step 3. Identify controls. Step 3 involves identifying all controls for material unwanted events, MUEs, encompassing both existing and potential new controls. This comprehensive identification is a critical precursor to selecting which controls are truly critical in the next step. It's like gathering all possible tools before choosing the most effective ones. In most cases, controls already exist from previous risk assessments, industry experience, or legislative requirements. Each identified MUE should be reviewed to ensure appropriate controls are in place. A key tool for this stage is the bowtie diagram, which visually maps hazards, causes, controls, and consequences, providing a holistic view of risk management. What constitutes a good control? Deciding what qualifies as a control is a crucial step in CCM. A good control must be a human act, an engineered object, or a system that actively prevents or mitigates an unwanted event. it must also have performance that can be specified, observed, measured, and audited. For example, a safety procedure is a control if its adherence can be verified. It is important to differentiate true controls from other important health and safety management system elements that are not controls themselves. Management plans, risk assessment techniques like Step Back 5x5, and behavior-based safety tools are valuable, but do not directly prevent or mitigate an MUE. They might describe controls or help identify them, but they are not the controls themselves. A good control is specific, measurable, and verifiable in its performance. Bowtie analysis for controls. Developing a bowtie diagram is a critical stage in identifying and assessing controls. It visually represents the relationship between a hazard, its causes, the unwanted event, and its consequences, with controls acting as barriers. While proprietary tools exist, bowties can also be drawn manually or using standard software, emphasizing the conceptual understanding over complex tools. Step 4. Select the critical controls. After identifying all controls using bowtie diagrams, Step 4 focuses on selecting the critical controls for each material unwanted event, MUE. This involves assessing each control against specific criteria to determine its criticality. The goal is to identify the critical few controls that, when effectively managed, can significantly reduce MUE risk. Critical Control Decision Tree. The Critical Control Decision Tree, often provided by organizations like ICMM members, is a valuable tool to help determine if a control is critical. This decision tree provides a structured, iterative process for reviewing various aspects of a control before making a final determination. It ensures consistency and rigor in the selection process. Step 5. Define performance and reporting. Step 5 involves defining the objectives, performance requirements, and reporting mechanisms for each critical control. This ensures that controls are not only in place, but are also performing as intended. It's about setting clear expectations for how well a control should function. Step 6. Assign accountability. Assigning accountability is crucial for ensuring that critical controls are effectively managed and monitored. This step involves clearly defining who owns each material unwanted event, NUE, critical control and verification activity. Without clear ownership, controls can become neglected, increasing risk. Step 7. Site-specific implementation. Step 7 focuses on adapting corporate or business unit CCM strategies to site-specific contexts. While initial planning, steps 1 to 6, may occur at a higher organizational level, it is crucial to review and adjust these plans to ensure they are appropriate and applicable to the unique conditions of each site or asset. This iterative process ensures local relevance and effectiveness. Site-specific planning involves adjusting critical control definitions, performance information, and verification requirements to suit the local context. Establishing a strong foundation for CCM at the site level includes leadership buy-in, effective communication, and developing a deep understanding of critical controls among the workforce. This localized approach ensures that the CCM strategy is practical and implementable on the ground, addressing specific operational realities. Step 8. Verification and reporting. Step 8 involves implementing the verification activities defined in previous steps and reporting on the status of each critical control. This puts the verification and reporting plan into practice, ensuring that controls are continuously checked for effectiveness. Regular verification is the backbone of a proactive safety system. Information gathered on each critical control is reported to the critical control owner, who then reports to the MUE owner at a defined frequency. This information flow is designed for efficiency, highlighting variances between expected and actual performance. A traffic light reporting system, green for good, yellow for caution, red for action, is often used to succinctly communicate status, enabling quick identification of issues and triggering immediate action if performance drops below defined thresholds. Step 9. Response to inadequate performance. The final step, Step 9, addresses responses to inadequate critical control performance. Critical control and MUE owners must be aware of control performance, and if controls are underperforming or an incident occurs, immediate investigation and action are required to improve performance or remove critical status. This ensures continuous improvement and prevents recurrence. Key actions include taking action when performance is below the defined trigger threshold and investigating the causes of unacceptable performance. Information from these investigations should be used to continuously improve the CCM process. It's crucial not to assume controls are adequate just because no accidents have occurred. Verification is essential to detect underperformance before incidents happen. The investigation might also trigger a review of the MUE or the addition of a new MUE, leading back to Step 2 for a revised approach.